Welcome to Foundations of Data Mining, Statistics, Probability, and Inference. In this lecture, we're going to explore the statistical tools and concepts that underpin modern data science. As data becomes more central to decision-making in every industry, understanding how to work with it rigorously is essential. This presentation introduces key foundations such as descriptive statistics, probability theory, and statistical inference. These are not just abstract concepts, they're the principles behind the models, predictions, and visualizations we use in real-world data science. We'll see how to summarize data, measure uncertainty, and make informed conclusions from samples. Whether you're preparing for applied work in data analysis or looking to sharpen your theoretical understanding, this session will help you build the statistical mindset needed to responsibly interpret data. Foundations of Data Mining, Statistics, Probability, and Inference by the Programming Professor. Let's take a look at the outline for today's session. First, we'll start with data collection and sampling, how to gather data that accurately represents a population. Next, we'll dive into descriptive statistics and distributions, which help us understand the patterns and structure of our data. We'll then move into probability and its rules, giving us a framework for quantifying uncertainty. That naturally leads into probability distributions, including key ones like the binomial and normal distributions. After that, we'll explore inferential statistics, where we'll learn to generalize from sample data using hypothesis testing and confidence intervals. Finally, we'll look at inference for proportions and means, applying statistical theory to real-world questions. This outline reflects the statistical pipeline, from data gathering to summarizing to analyzing to drawing conclusions, all critical for data mining and scientific thinking. Statistics is a core component of data science, as it provides the framework for collecting, analyzing, and interpreting data. In practice, statistics empowers three major activities in data science. First, sampling helps us efficiently collect data that represents a larger population, which is especially important when studying entire populations is impractical or impossible. Second, descriptive statistics allow us to summarize and explore data through metrics like means, medians, and standard deviations. This gives us an initial understanding of patterns or anomalies in the data. Third, inferential statistics allow us to go beyond the sample and make claims about the broader population. This is where confidence intervals and hypothesis tests come into play. Additionally, statistical models help us make data-driven decisions by estimating trends, testing assumptions, and forecasting outcomes. Ultimately, applying the correct statistical tools helps ensure that our analyses are responsible, transparent, and backed by evidence, qualities essential for any data scientist. To draw valid conclusions from data, we need to understand the sampling process. A population is the full group we're interested in studying, while an observational unit is a single member of that group, like one person, product, or event. Since analyzing an entire population is often unrealistic, we collect a sample which is a subset of the population. The number of units in that sample is called the sample size, denoted by n. Sampling is necessary because of constraints like cost, time, or access, but the key challenge is ensuring the sample is representative of the population. If it's not, any conclusions we draw could be biased or misleading. A well-designed sample should capture the diversity and structure of the population so that we can apply statistical inference later. This is a foundational principle in both statistics and data science. The quality of your sample directly impacts the quality of your analysis. There are several common sampling methods, each with its strengths and limitations. Random sampling is the gold standard, where every subset of the population has an equal chance of being selected. This approach minimizes bias and supports strong generalization. Stratified sampling divides the population into distinct groups or strata, and then samples within each group, useful when we want representation from specific subgroups. Cluster sampling also divides the population, but instead of sampling from every group, we randomly select whole clusters and study them in full. Systematic sampling selects every kth item from a list after a random starting point, efficient but less random. Finally, convenience sampling selects units that are easy to access, such as surveying nearby people or using available data. While tempting, convenience sampling is not recommended because it introduces serious bias and undermines the validity of statistical inference. Choosing the right sampling method is a critical early decision in any data-driven study. In statistics, it's important to distinguish between observational studies and experiments, as each provides different types of insights. An observational study involves recording data without manipulating any variables. For example, collecting housing prices and features from existing real estate listings is observational. You're simply measuring what already exists. In contrast, an experiment involves applying treatments and then observing the outcomes. A common example is an A/B test, in which users are randomly assigned to two different versions of a website to measure which design leads to more clicks. The key feature of an experiment is random assignment of treatments, which helps eliminate confounding variables and allows researchers to draw causal conclusions. Observational studies can reveal associations but not causation, whereas experiments are designed specifically to test causal effects. Understanding the distinction is essential when designing studies or evaluating the strength of a statistical claim. When working with real datasets, you often need to create samples in code. Python's pandas library makes random sampling straightforward using the sample method on a data frame. You can sample a fixed number of rows using the n parameter or a percentage of the data using frac. The replace option controls whether the sampling is done with or without replacement, and random state sets a seed to make the results reproducible. For example, sampling 5 rows without replacement is done with df.sample n equals 5, while sampling 20% of the data with replacement and reproducibility uses df.sample, frac equals 0.2, replace equals true, random state equals 42. These tools are especially helpful when simulating data collection, bootstrapping, or preparing training and testing subsets in machine learning. Being able to generate random samples programmatically is a key skill in data science, supporting both theoretical analysis and practical workflows. After collecting data, one of the first steps is to summarize and describe its features using descriptive statistics. A feature or variable is any measurable characteristic of an observational unit, such as height, income, or temperature. Descriptive statistics help us understand the distribution of a feature, meaning the possible values it can take and how frequently each value occurs. By analyzing a feature's distribution, we can detect clusters, gaps, outliers in the shape of the data. For example, some distributions may be symmetrical, while others may be skewed or contain heavy tails. Visualizing the distribution, through histograms, boxplots, or density plots, is crucial for identifying patterns that might not be obvious from raw numbers alone. This early stage of analysis guides decisions about which statistical methods or models to apply next, and helps avoid errors caused by overlooking structure or variation in the data. One of the key goals of descriptive statistics is to summarize the center of a distribution, which gives us a sense of where most values are located. The two most common measures of center are the mean and the median. The mean is calculated by summing all values and dividing by the number of observations. It is widely used but sensitive to extreme values, also known as outliers. The median, on the other hand, is the middle value in a sorted list and is more robust to skewed data. For example, in the dataset 10, 12, 14, both the mean and median are 12. But in 10, 12, 100, the mean is pulled up to about 40.7 while the median remains at 12. That's why for symmetric distributions, the mean is preferred, while for skewed distributions, the median often gives a more accurate picture of the data's typical value. Choosing the right measure of center is key to proper interpretation. Beyond the center, we also care about the spread of a distribution, which tells us how much the data varies. There are several common ways to measure spread. The range is the simplest. It's the difference between the maximum and minimum values. The interquartile range, IQR, focuses on the middle 50% of the data, offering a more robust view by excluding outliers. More advanced measures include variance and standard deviation. The variance calculates the average of the squared differences between each value and the mean. The standard deviation is simply the square root of the variance, putting the units back on the same scale as the data. These measures help quantify how tightly or loosely data points are clustered around the center. For example, a low standard deviation means most data points are close to the mean, while a high standard deviation suggests wider variability. Understanding spread is crucial for assessing risk, uncertainty, and consistency in data-driven decisions. In addition to center and spread, we also use measures of position and shape to better understand how data behaves. Quantiles divide the data into parts based on rank. For instance, the median is the 0.5 quantile, meaning half the values fall below it. Other quantiles include quartiles, percentiles, and deciles. These help identify where a particular value stands within the distribution. Another useful tool is the z-score, which tells you how many standard deviations a data point is from the mean. A z-score of +2 means the value is 2 standard deviations above the mean. This is helpful for detecting unusual values or comparing across distributions. Measures of shape describe the overall form of the distribution. Skewness measures asymmetry. A positive skew has a long right tail, and a negative skew has a long left tail. Kurtosis measures the heaviness of the tails. High kurtosis means more extreme values. Understanding shape helps identify patterns, potential outliers, and whether your data meets the assumptions of statistical models. In Python, computing descriptive statistics is straightforward using pandas, which offers a range of built-in methods for summarizing data. You can load a dataset with pd.read_csv, and then use methods like mean, std, and quantile to calculate central tendency, spread, and position metrics. For a quick overview, df.describe provides a summary table with key statistics like count, mean, standard deviation, min, max, and quartiles. More specific methods like skew and kurtosis offer insight into the shape of your distribution. These tools allow for fast, reproducible exploratory data analysis and are foundational for both standalone statistics projects and machine learning workflows. Whether you're analyzing housing prices, customer ratings, or test scores, Pandas enables you to quickly assess distributions and detect issues like outliers or skewed data. Descriptive statistics in Python give you a practical, hands-on way to interact with real data, preparing it for deeper analysis. Probability is the mathematical framework that helps us quantify uncertainty in data science. It's foundational to inferential statistics because it allows us to model random processes and make predictions. Probabilities range from 0 impossible to 1 certain, and they help us evaluate the likelihood of different outcomes. Some key terms include a random process, which is any process that leads to unpredictable outcomes, an outcome, which is a single possible result, and a sample space, which is the set of all possible outcomes. An event is a specific subset of outcomes we're interested in, like flipping heads on a coin. The probability of an event, denoted P of A, is calculated as the number of favorable outcomes divided by the total number of outcomes. We often interpret probability as long-run frequency. For example, if you flip a fair coin many times, the proportion of heads will approach 0.5. This concept is the bridge between randomness and predictability in data. To work with probabilities effectively, we also need to understand event operations, which help us analyze relationships between events. The complement of an event A, written as A raised to C, includes all outcomes not in. The union of events A and B, written A union B, includes all outcomes that are in A, B, or both. The intersection, written A intersection B, includes only those outcomes that are in both A and B. Events are disjoint if they cannot happen at the same time, meaning A intersection B is the empty set. For example, let A be household size greater or equal to 4 and B be income greater or equal to $75,000. The intersection of A and B represents households that are both large and high income. Understanding these relationships is critical for combining probabilities and reasoning about joint or overlapping scenarios. These operations are used throughout probability theory, including when calculating risk, modeling uncertainty, or making data-driven decisions. Now that we understand how events work, we can apply the rules of probability to calculate specific values. First, there are three basic axioms. 1. Probabilities must be greater than or equal to 0. 2. The probability of the entire sample space is 1. And 3. For disjoint events, the probability of A or B happening is the sum of their individual probabilities. P of A union B equals P of A plus P of B. Beyond these axioms, we also use the complement rule, which says P of AC equals 1 minus P of A. This is useful when it's easier to calculate the opposite of an event. The general union rule applies when events are not disjoint. P of A union B equals P of A plus P of B minus P of A intersection B. Lastly, for independent events, where one doesn't affect the other, the probability of both happening is the product. P of A intersection B equals P of A times P of B. These rules form the foundation for more advanced topics like conditional probability, Bayesian inference, and statistical modeling. Conditional probability allows us to update our understanding of one event based on the occurrence of another. It represents the probability of event A happening given that event B has occurred and is written as P of A given B. The formula is P of A given B equals P of A intersection B divided by P of B, meaning we divide the probability that both A and B happen by the probability that B happens. For example, suppose you're interested in the probability that an email is spam given that it contains a link. If you already know how often emails with links are spam, P of A intersection B, and how often emails contain links, P of B, you can use this formula to calculate the conditional probability. In the case of independent events, where one event doesn't influence the other, the conditional probability simplifies. P of A given B equals P of A. Conditional probability is fundamental to many machine learning algorithms, including naive Bayes classifiers, and plays a key role in evaluating dependencies between features in real-world data. Bayes' rule builds on conditional probability and gives us a way to reverse the direction of conditional statements. It's especially helpful when we want to know P of A given B, but only have access to P of B given A. The formula is P of A given B equals P of B given A times P of A divided by P of B. This rule is useful in many real-world scenarios. Take, for example, spam detection again. Suppose you want to know the probability that an email is spam given it contains a link. Bayes' rule allows you to calculate that using the probability of a link given spam, the overall probability of spam, and the overall probability of a link. This reversal is what makes Bayes' rule powerful. It allows you to infer cause from effect when the effect is easier to measure. It's widely used in diagnostics, forecasting, and classification problems in data science. The ability to reverse and update probabilities is essential for building dynamic models that learn from new evidence. A random variable is a function that assigns numerical values to the outcomes of a random process. We typically denote random variables with capital letters like X, Y, or Z. There are two main types of random variables. Discrete random variables take on countable values, such as the number of children in a household or the result of rolling a die. Continuous random variables, on the other hand, can take on any value within an interval, such as weight, height, or body mass index. Each type of random variable has a corresponding probability distribution that describes how likely different values are. For example, a distribution might tell us that a household size of 4 is more common than 1 or 7. Understanding the type of random variable you're working with helps you choose the right statistical tools. For instance, the binomial distribution is for discrete counts, while the normal distribution models continuous outcomes. The Bernoulli distribution is one of the simplest and most fundamental probability distributions in statistics. It models a binary outcome, meaning there are only two possible results, often coded as 1 for success and 0 for failure. If X is a Bernoulli random variable, we write it as X is distributed as Bernoulli with parameter P, where P is the probability of success. For example, you could define x equals 1 if a student passed a class and x equals 0 otherwise. The Bernoulli distribution is incredibly useful in practice because many situations naturally involve yes-no outcomes. Click or no click, converted or not, survived or died. It's also the building block for more complex models like the binomial distribution, which aggregates many independent Bernoulli trials. In data science, Bernoulli models are used in classification, A/B testing, and logistic regression, making them a foundational concept for analyzing binary outcomes. Building on the Bernoulli distribution, the binomial distribution models the number of successes in a fixed number of independent Bernoulli trials. We write this as x is distributed as binomial with parameters n and p, where n is the number of trials and p is the probability of success in each trial. For example, if you select 25 students and count how many passed an exam, the number of passes would follow a binomial distribution. The binomial model assumes each trial is independent and has the same probability of success. It's used in many real-world applications: quality control in manufacturing, biological experiments, and even sports analytics. In data science, it's especially helpful in modeling proportions, such as the fraction of customers who click an ad or convert after visiting a web page. The binomial distribution allows us to calculate the likelihood of different outcomes, construct confidence intervals, and perform hypothesis tests on binary data. The normal distribution is one of the most widely used and important distributions in statistics. It's a continuous, symmetric, bell-shaped curve that models many natural phenomena, such as heights, test scores, and measurement errors. We denote it as x is distributed as normal with parameters mu and sigma, where mu is the mean, representing the center, and sigma is the standard deviation, representing the spread. Most data points fall near the mean, with fewer values appearing as you move further out into the tails. A special case is the standard normal distribution, where the mean is 0 and the standard deviation is 1. Any normally distributed variable can be standardized using the formula z equals x minus mu divided by sigma. This transformation allows us to use standard normal tables and perform consistent probability calculations. The normal distribution underpins many inferential techniques, including confidence intervals and hypothesis testing, due to its well-defined mathematical properties and the central role it plays in the Central Limit Theorem. The t-distribution is closely related to the normal distribution but has slightly heavier tails, which means it accounts for more variability in the data, especially useful when working with small sample sizes. It's symmetric and bell-shaped like the normal curve, but it is governed by an additional parameter called degrees of freedom, df. As the degrees of freedom increase, the t-distribution becomes closer to the standard normal distribution. The t-distribution is typically used when the population's standard deviation is unknown, which is often the case in real-world scenarios. For example, when estimating the average test score from a small group of students, we would use the t-distribution instead of the normal distribution. This flexibility makes it ideal for constructing confidence intervals and performing hypothesis tests with small samples. It's a key tool in inferential statistics and serves as the basis for t-tests, which are common in scientific research and data analysis. Python makes it easy to work with probability distributions using the SciPy.stats module. This module includes built-in functions for commonly used distributions like Bernoulli, binomial, normal, and t-distributions. For the Bernoulli distribution, you can use PMF to compute the probability of a specific outcome and CDF to compute the cumulative probability up to a certain value. The binomial distribution includes similar functions, but requires you to specify the number of trials and the success probability. The normal distribution functions include PDF to calculate the probability density at a value and CDF to find the probability of observing a value less than or equal to a given number. For the t-distribution, you specify the degrees of freedom and use similar functions. These tools allow you to model real-world processes and perform statistical computations programmatically. With SciPy.stats, data scientists can easily calculate probabilities, simulate data, and build robust statistical models. Inferential statistics enable us to generalize from sample data to an entire population, which is a critical goal in data science. Rather than analyzing every single data point in a population, which is often impossible, we take a sample and use statistical methods to draw conclusions. There are two main types of inference. The first is hypothesis testing, which evaluates specific claims about a population, such as whether a new product performs better than the old one. The second is estimation, where we calculate a likely range for a population parameter using techniques like confidence intervals. These methods depend on understanding variability and uncertainty in the data. A parameter is a fixed but usually unknown value about a population, like the true average commute time or the proportion of users who churn. Inferential statistics give us tools to estimate these values and test assumptions, forming the backbone of decision-making in data-driven environments. To make reliable inferences, we rely on the concept of a sampling distribution. A sampling distribution represents the distribution of a statistic, such as the sample mean or sample proportion, across many random samples from the same population. For example, if you collect 100 different samples of commute times and compute the mean for each one, the set of those means forms a sampling distribution. This concept is crucial because even if each sample is different, the distribution of all possible sample statistics reveals how accurate our estimates are likely to be. It allows us to measure sampling variability, calculate standard errors, and assess how likely our results are under a given hypothesis. The sampling distribution forms the basis for constructing confidence intervals and conducting hypothesis tests. Understanding this concept helps you recognize the difference between a single sample's estimate and the variability you'd expect across repeated experiments. The Central Limit Theorem, CLT, is one of the most important results in all of statistics. It tells us that if we take sufficiently large random samples from any population, the distribution of the sample mean will be approximately normal, regardless of the population's original distribution. This is incredibly powerful because it allows us to use normal-based inference techniques, even when the original data is not normally distributed. The CLT applies to both sample means and sample proportions, and it's what justifies using z-scores, confidence intervals, and hypothesis tests in many practical situations. The rule of thumb is that the sample size should be large enough, typically n greater or equal to 30 for the CLT to hold. This theorem gives us a foundation for statistical inference, allowing us to measure uncertainty and draw conclusions about populations using familiar and mathematically tractable methods, even when the underlying data isn't perfect. Hypothesis testing is a formal statistical process used to evaluate whether there is evidence in sample data to reject a claim about a population. The first step is to state the null hypothesis, H0, which represents the default assumption, and the alternative hypothesis, which represents the research question or claim we are testing. Next, we calculate a statistic, such as a sample mean or proportion, and determine the p-value, which tells us how likely we would be to observe a result this extreme if H0 were true. Based on the p-value, we make a decision. Reject H0 if the p-value is small, typically less or equal to 0.05, or fail to reject H0 if the p-value is large. The goal of hypothesis testing is to determine whether the observed data provides strong enough evidence to support the alternative hypothesis. This framework is used widely across research, business, and data science to make informed, data-driven decisions. When performing hypothesis tests, it's important to understand the potential for type 1 and type 2 errors. These occur when our decision from the test doesn't match reality. A type 1 error happens when we reject the null hypothesis even though it is actually true. This is considered a false positive, and the significance level alpha, often set at 0.05, is the maximum acceptable probability of making this type of error. A type 2 error happens when we fail to reject the null hypothesis even though the alternative is true, which is a false negative. In practice, there's a trade-off between these two types of errors. Reducing one can increase the other. For example, lowering alpha reduces the chance of a type 1 error, but may increase the chance of a type 2 error unless the sample size is increased. Understanding these errors is critical when interpreting p-values and making decisions based on statistical tests, especially when the consequences of false positives or false negatives are high. Estimation provides a way to quantify uncertainty by constructing confidence intervals around sample statistics. A confidence interval CI gives a likely range of values for a population parameter, such as the true mean or proportion, and is calculated using the formula statistic plus or minus margin of error. The margin of error is the product of a critical value, which depends on the desired confidence level, and the standard error, which reflects sampling variability. For example, a 95% confidence interval means that if we took many samples and built intervals the same way, about 95% of those intervals would contain the true population parameter. Confidence intervals are more informative than single estimates because they express a range of plausible values, helping us assess the precision and reliability of our findings. They are widely used in reporting statistics across scientific research, policy analysis, and business analytics. Let's apply inference to a practical case, inference for one proportion. This method allows us to estimate or test a population proportion based on sample data. For example, suppose we know that 71.6% of homes in Iowa exceed a certain radon level. A researcher collects a sample of 351 homes in northwest Iowa and finds that 285 exceed that level. The question is, does this region have a significantly different proportion than the statewide value of 0.716? We can approach this in two ways. First, we can construct a confidence interval around the sample proportion to see if it includes the state value. Second, we can perform a hypothesis test to determine whether the difference between the sample and the population is statistically significant. This kind of one-proportion inference is commonly used in surveys, polling, public health, and quality control, making it a foundational tool in applied statistics. When comparing two groups, we use inference for two proportions to determine whether the difference between the proportions is statistically significant. This method is ideal when you're examining outcomes across two independent samples. For example, in a radon exposure study of 621 homes, 351 homes yielded valid test results, while 270 were incomplete. Suppose we're interested in whether the proportion of homes with basements differs between these two groups. We calculate the sample proportions for each group and then perform a hypothesis test for the difference. H0, P1 equals P2 versus HA, P1 not equal to P2. The test evaluates whether the observed difference in proportions is greater than what we'd expect from sampling variability alone. This technique is commonly used in public health, marketing experiments, and social sciences to compare behaviors, responses, or characteristics across distinct populations or treatment conditions. When dealing with numerical data, we often want to estimate or test claims about the population mean, which leads us to inference for one mean. In cases where the population standard deviation is unknown, which is typical, we use the t-distribution. For example, suppose we want to test whether the user-reported fuel economy for the 2019 RAV4 hybrid matches the EPA estimate of 40 mpg. A sample of 14 user-reported mpg values is collected. We calculate the sample mean and standard deviation, then perform a one-sample t-test to determine whether the observed sample provides enough evidence to say the true mean is different from the EPA's claim. This process illustrates how inferential statistics are used in real-world scenarios to evaluate product claims, monitor performance, and guide data-driven decisions. To compare the means of two independent groups, we use a two-sample t-test. This test is appropriate when we want to determine whether the difference between two sample means is statistically significant. For instance, suppose we collect user-reported miles per gallon mpg for the 2019 and 2020 RAV4 hybrid models. Let's say the 2019 group has 14 samples and the 2020 group has 8. We want to test whether the average mpg differs between the two model years. The two-sample t-test evaluates the null hypothesis that the population means are equal H0, mu1 equals mu2 using the observed sample data. This method is widely used in A/B testing, clinical trials, and product comparisons. It assumes that the two groups are independent and that the data in each group are approximately normally distributed. By comparing means across groups, we gain insight into whether observed differences are due to chance or reflect meaningful variation. In Python, you can perform inference for proportions using the statsmodels.stats.proportion module. The function proportion ztest is used to test one or two sample proportions. It requires the number of successes count, the number of observations knobs, the value to test against, and the direction of the test alternative. For example, to test whether the sample proportion of radon-exceeding homes is different from the state level of 0.716, you'd call proportion ztest 285, 351, value equals 0.716. This function returns the z-statistic and p-value, which you can use to draw a conclusion about statistical significance. You can also construct a confidence interval for the proportion using proportion confint. These tools make it easy to implement proportion-based inference in code, supporting fast, reproducible statistical analysis across a wide range of applications in business, healthcare, and environmental studies. For inference involving means, Python offers tools in the SciPy.stats module. The function t-test one-samp performs a one-sample t-test, allowing you to test whether the sample mean differs from a known value. You provide the sample data and the population mean, and it returns the t-statistic and p-value. For comparing two independent samples, you use t-test-ind, which compares group means and accounts for unequal variances when needed. For example, you could use t-test one-samp to test if the average user-reported MPG matches 40, and t-test-ind to compare the MPGs of two RAV4 models. These tools allow you to conduct rigorous statistical inference directly within your Python workflow, integrating seamlessly with pandas and NumPy for data preprocessing. Being able to perform t-tests in code equips you to apply statistical reasoning in real-world analysis, from testing product performance to evaluating experimental results. To wrap up, let's review the key ideas from this presentation. Statistics provides the essential foundation for all stages of the data science lifecycle, from collecting data to modeling and interpreting results. We began with descriptive statistics, which help us summarize features of data using measures of center, spread, and shape. We then explored probability, which gives us a framework for quantifying uncertainty and reasoning about chance events. Named distributions like Bernoulli, binomial, normal, and t-distributions are central tools in modeling data and making predictions. Finally, we examined inferential statistics, which allow us to generalize findings from samples to populations through techniques like hypothesis testing and confidence intervals. These methods support data-driven decision-making and help us understand the reliability of our conclusions. Throughout, we've also seen how Python libraries like pandas, SciPy, and statsmodels streamline these statistical computations, making them accessible, reproducible, and scalable. By mastering these foundational concepts, you're better equipped to approach real-world data with confidence, draw valid insights, and apply statistical thinking across a wide range of domains in data science.
Thanks for watching. Let me know in the comments if there are other topics you would like me to talk about. If you enjoyed this video, please like, share, and subscribe for more content on software engineering and technology. See you next time.